All right, good afternoon. We are mitigators, and this is our project for mitigating the lunar plume upon arrival to the moon. Here's a quick overview of our presentation. We have the overview of our mission, and then we have the overview of our design, which includes things like structures, thermal analysis, electrical analysis, fluid analysis, and then the overall design. Our mission is to reduce to a maximum the amount of lunar plume that can be damaging to the spacecraft and the surroundings while landing on the moon for many different reasons that I'll get into right now. So this is a quick background on lunar regolith. The main aspect of lunar regolith that our design seeks to mitigate is lunar dust, which is between 0 and 50 micrometers, with a peak at around 10 micrometers, so the majority of particles are around there. There's also lunar soil, but that's larger particles, which our design can mitigate, but the majority of what we're trying to do is the lunar dust, because we see that as a bigger threat. Visibility concerns were addressed in our design ideas due to many different missions landing on the moon, and right before they touch down, there's no visibility, so we wanted to try to reduce that. Will increase the visibility. The dangers of the regolith are very prevalent. Apollo 12 had a mission where when they landed, the Surveyor 3 drone that was 525 feet away got hit by the plume coming out from the landing, which is very important, especially considering the future moon missions where there will be a lunar colony. And if you land and the regolith goes everywhere, then you can destroy the environment that we have created on the moon. The lander we have chosen is the HLS from SpaceX. We chose this specific design because of the top-mounted motors, which already create a sort of dust mitigation due to the angle. Instead of having one powerful thrust right before landing, you have a separated thrust that is above the mid-body of the spacecraft that is angled outward. One thing to note is that SpaceX is a private company, so all our estimations and all our design is based on the renders and the public information that is available. Without that information, with more information, we could do a better job, that's for sure. We want to try to reduce the diffuse gas eruption and the diffusion-driven shearing effects mostly.
Hi, I'm Chris, and I'm going to be talking about our design today. So the core ethos of our design comes from a Washington State University study, which found a 98% reduction rate in lunar regolith when using liquid nitrogen in a vacuum environment. This is a photo from their study. As you can see, this is before and after a liquid nitrogen treatment. So this 98% effective rate was actually the most successful technique that they've found to date. And so we use this as kind of the core for our design. So with that being said, we came up with a nozzle design, or I should say a system of nozzles. We have about 50 in circumference around the hull of the HLS. And upon descent and ascent to the lunar surface, these nozzles will spray liquid nitrogen, and which forms a protective barrier around the HLS. The high speeds of the liquid nitrogen coming out of the nozzles reflect any lunar regolith that would otherwise approach the HLS. And also a big portion of our design, which we thought was really important, was to make it as least intrusive as possible. So for that, we developed a latch mechanism where the nozzles are actually seamless with the hull until descent. Upon use, the AM stepper motor in our design will move the latches outwards, and the nozzles will then eject the liquid nitrogen. And then once landed, they'll come back into the hull. This was really attractive to us because it allowed us to maintain the seamless nature of the HLS, and so it wouldn't interfere with other landing and docking operations. So yeah, and thank you. Next.
All right, so in terms of the CAD model for our design, we're using a supersonic, a converging diverging supersonic nozzle, as you can see here. So this square base is a representation of the outer shell of the rocket ship. It's actually made out of stainless steel, and like, of course, the rocket ship itself has like a 9-meter diameter, which is approximately 30 feet. So it has about a 28.27 meter circumference. So for practical applications, this wasn't modeled on the CAD design, but just know if it were to be manufactured, this piece would be would have a slight curvature to it. Right. So the supersonic nozzle is utilizing a hatchet door mechanism. So this is the inside of the rocket ship, right? So we have a AM stepper motor manufactured by the company Fallhaber that's mounted on the inside, as well as a female hinge here and a male hinge. So the stepper motor has a square cross section, right, that feeds into the male hinge, and the male hinge has a circular cross section that feeds into the female hinge. So the female hinge and the stepper motor are actually mounted on the inside of the Starship SpaceX HLS, while the male one is actually the one that's rotating and that's pivoting and that's moving the hatchet door, right? So the fillets, we've created fillets here on the bottom and the top of this door, as well as, you can't see it really, but inside of the stainless steel plate, there's fillets so that the design can open up 90 degrees. So on the bottom surface of the Starship, basically the hatch doors are opening 90 degrees, and the nozzle can expunge the liquid nitrogen. A few other parts to notice, of course, there has to be some tubing feeding into the inside this nozzle. So right here, that's inside component. And we, of course, need insulation, right? So we've discussed a few different materials, such as aerogels, foams, or multi-layer insulation in order to create that vacuum, because of course, there's some heat transfer components to this because of the cold temperatures that we're expunging the liquid nitrogen, as well as we don't want to get, any of the internal components of the Starship damaged. So we have to account for that. We also have to account for the vacuum of space. But besides that, that's basically the preliminary CAD model that we have set up.
I'm going to delve into the more specifics of the materials and the costs. We chose to use 50 convergent divergent nozzles, which are made of TZM alloy. The length of the nozzle itself is roughly 16.5 centimeters, and the outlet width is roughly 20.3 centimeters. The inlet diameter is about 4 centimeters. And the TZM alloy is good for space because it has a high yield strength and a high elastic modulus at high temperatures. The motor hinge and motor mount that Jason was just talking about is made of AISI 304, which is lightweight and corrosion resistance at high temperatures, making it optimal for space. And the door mechanism that would open and close our device is made of 2024 alloy, which is also has a high yield strength and is fatigue resistance. The motor is the series AM3248, which has a holding torque of roughly 152 millinewton meters. And the attachments we have are bolts and welding. The bolts are used for the motor to mount the motor, and it is a grade 12.9 and about a size M3 by 4.7 millimeters. Our welding is friction stir welding, which uses a non-consumable tool and friction heat to weld our two pieces together. The tank is the Duracell 230 LN2 tank, which when full of liquid nitrogen weighs approximately 330 kilograms. It's going to be stored in the payload area and won't take up much space as it is 142 centimeters in height and 66 centimeters in diameter. To get the liquid nitrogen from the tank to the nozzle band, we have reinforced rubber pipes that run the 20 meters, and they are approximately 5 centimeters in diameter. The reinforced rubber allows our liquid nitrogen to stay pressurized and cool, so it releases at the most optimal state it should. We have 3 types of valves that we'll also be using: emergency valves, pressure reduction valves, and quick release valves. Our approximate cost is $35,000, but that is before implementation and integration into the Starship, as there's not much knowledge available for public domain. We're not too sure how we could integrate this into the Starship HLS until SpaceX releases more information. So for now, our approximate cost is about $35,000.
So I will talk about the fluid analysis. The fluid analysis is specific to the fluid analysis of the actual nozzle and the design we used. So some basic information. We decided that the plenum used for the nozzle will contain nitrogen at 72 Kelvin and would have a total pressure of about 100 kilopascals. This is to keep the nitrogen in a liquid state at all times within the tank. The nozzles were designed to have an exit Mach number of 3.49, and each nozzle should have a mass flow rate of about 0.0660 kilograms per second. To completely finish the nozzle design, we needed to understand how many nozzles there would be on the HLS rocket. To determine that, we needed a CFD plot of the weight of the nozzles to determine how the spread and how much we would need to cover the entire circumference. So here is a Mach number contour plot of our nozzle. As you can see, the wake extends to about 3 nozzle diameters outside of the center line of the nozzle. This is a 2D representation of the nozzle from above. As you can see here, the wake has a medium Mach number of about 0.6 to 0.8. So it's still going incredibly fast. And it extends 3 diameters out, which means that less nozzles would be needed to use. So the CFD gave us that our expanded Mach number would be only 2.17, which is far below what our expected Mach number was using compressible flow theory. And we determined that that was because of density attenuation caused by the vacuum of space. Next, we have, I will explain more of the CFD results. So the nozzle wake extends, as I said before, 3 nozzle diameters outside. And the total length covered by one of these nozzles is 61 centimeters. So in total, 50 nozzles would be needed to completely cover the entire circumference of the rocket body. As I said before, the estimated Mach number is below the design value, and all 50 nozzles would be using up 3.3 kilograms per second of nitrogen when they are being used. So this comes to our results, which is the tank analysis. For a 10-second entry and exit burn, we determined that 66 kilograms of nitrogen would be needed. To ensure that we had enough nitrogen just in case of emergencies caused when landing or leaving the planet or the moon, we decided that a factor of safety of 1.5 would be established, and that would mean that our tank would need a storage of 100 kilograms. This is a picture of a type of tank that could be used. These are for storing cryogenic liquids. With an ideal gas approximation, we determined that the nitrogen would be about 80.7 liters in total. Okay.
So now that we know a little bit more about the tank, let's delve into the fluid system overview. So the first part of the fluid system is the liquid nitrogen storage tank itself. So there's 4 main components that are part of the liquid nitrogen storage tank. So that is the pressure building coil, the pressure gauge, the thermocouple, and a gas release valve. So these 4 components are all part of the liquid nitrogen storage tank. So the liquid nitrogen storage tank pressure building coil will allow the liquid nitrogen to be kept at the required pressure, which was 100 kilopascals, constantly. And this can be monitored by the pressure gauges. So the pressure gauges will ensure that the pressure building coil is maintaining the liquid nitrogen at the proper pressure. The thermocouple, this is to make sure that the liquid nitrogen stays at the correct temperature for use, just to make sure that the liquid nitrogen does not fluctuate in pressure too much, and which would cause instability to the system. And the 4th element of the liquid nitrogen storage tank was the gas use valve. So that allows for the liquid nitrogen to go from the liquid nitrogen state inside the tank and to be expelled by the nozzles in the gas state. So these 4 systems comprise of the liquid nitrogen storage tank. And outside or in conjunction to this, there is an emergency shutdown valve. So this emergency shutdown valve ensures that the liquid nitrogen, if there were any complications, if there was a rupture, or if there were any leaks, or if there was any sort of complication to the storage tank itself, or to any of the components that are a part of the storage tank, the emergency shutdown valve would activate, and that would stop the liquid nitrogen from going anywhere else inside the spacecraft, and specifically out to the nozzles. After the emergency shutdown valve, there's also a pressure reduction valve. So this pressure reduction valve allows the liquid nitrogen that is expelled through the nozzles to not fluctuate from any drastic pressure fluctuations caused by the storage tank. So if there are any fluctuations from the storage tank or anything upstream of the pressure reduction valve, this pressure reduction valve will ensure that none of those fluctuations affect anything downstream. So this is also monitored by a pressure gauge. So the pressure gauge will ensure that everything that comes after, or the liquid nitrogen that comes out of the pressure reduction valve, is maintained at the correct pressure. And if there are any fluctuations, then the pressure gauge can monitor that from the pressure reduction valve. So after the pressure gauge, this leads to the 50 quick release valves that lead to the 50 nozzles. So these 50 quick release valves allow for the rapid expulsion of the liquid nitrogen, or of the gaseous nitrogen, out of the nozzles. So each one of these quick release valves are also monitored by pressure gauges. This is a key part of this system, as if there are any faults with any of the nozzles. So if there's any faults to one or a couple or a few of these nozzles, then these pressure gauges can monitor whatever fluctuations is going on. And if there is a nozzle that is not performing correctly, then the pressure gauges can monitor that, and the quick release valves for whichever nozzles that are not performing as they should be, they can be shut down. And those and the spacecraft can be still protected by all of the nozzles that are functioning correctly.
All right, so I'll go ahead and kick off the structural analysis by discussing the attachment methods. We primarily analyzed two different attachment methods, fasteners like bolts and screws, as well as welding. We found that fasteners allow for very easy disassembly if any components need to be repaired or replaced, and also are very cost-effective when it comes to implementation. However, with a lot of fasteners, this will add a lot of weight to the spacecraft, which will incur a lot of cost. Not to mention, fasteners also need to be regularly retightened to cope with the loosening that can occur from vibrations during launch, landing, and then general operation. As well as the fasteners need to be properly torqued to ensure there's not additional stresses at the attachment points. On the other hand, welding requires less hardware, which makes it very efficient when it comes to weight reduction. But it's very difficult to disassemble a weld, making any kind of repair, replacement, or modification of a component that's welded a lot more costly, and it requires high skill to implement a weld due to the high detail and precision that is required when welding. So with this information, we decided to implement fasteners in as few places as possible to try and save as much weight as we could. So we utilize bolts primarily just for the motors, attaching them to the motor mounts, which allows for accurate alignment, as well as any kind of repairs or replacements that need to be made to the motors are very easy and cost effective. And then we apply welding for most of the other components, as it reduces the weight and it's very strong and durable.
To determine the force caused by the nozzle, we used a simple compressible flow estimation using the integral form of the momentum equation to determine that the force caused by each nozzle would be about 190 newtons. And this would be in the direction shown in the figure above.
So for our structural analysis, we chose 3 points to perform our structural analysis on. So these 3 points were chosen because each point we determine if these 3 points fail, it will cause significant impact to the nozzle performance itself. So the first point, which is point A, this is the square shaft base. So this is the motor shaft that connects into the system that rotates the nozzle itself. So if this component fails, then the the rotation ability of the nozzle would be severely impacted, and the nozzle would not be able to rotate, which is why we chose that as our first point. The second point that we chose was the nozzle to weld support, which is the weld that connects the base to the nozzle. So the base has an extrude that connects to the nozzle, and that portion is welded. So we chose that as our second point because as it is a weld and those two parts, the nozzle and the base, are not machined together, this could cause significant problems if it did fail here. This would cause the nozzle to rip from the base, and then the nozzle would not be connected to the base anymore. So this is why we chose this point as our second point to conduct structural analyses on. And our last point was the weld support to the base. So this point is the point where the base, the extrude connects to the actual base itself. So this point we chose because if this point were to fail, this would rip the nozzle from the base itself. So the nozzle would be able to freely rotate at any angle, at any degree, and this could cause severe implications for the rest of the system.
So I'm just gonna go over the structural calculations that we did for the static points of failure that Meyer just outlined. So for the square, for all of these structural calculations, we used Tresker failure theory, the more conservative approach. For the square shaft base, we found a max shear using Tresker failure theory of 50.86 megapascals. The allowable shear based on the material used is 386 megapascals. So our maximum shear is well within our allowable shear. The nozzle to weld support and the nozzle to base support both had the same allowable shear of 124 megapascals, and the force from the nozzle induces a moment onto these 2 points, and from Tresker's failure theory, we found that the max shear is really minimal at 0.526 MPa and 0.525 MPa. Those are also well within the allowable shear range. So from these calculations, there is very minimal to no risk of failure from the force induced by the nozzle flow.
In addition, we did some dynamic loading calculations for the motor itself to see if the use of the stepper motor would cause fatigue or perhaps even fail while working. Since we have a very small window of operations, the SN and the SN curve led the dynamic loading to have infinite life, so it would never see enough stress to cause the cracks and things like that. However, we did find that the dynamic loading was around 6.2 megapascals, which is a very small proportion of the shaft ultimate strength and of the shaft yield strength.
Yeah, so for the thermal analysis, first we determined that the thermal conductivity of the TZM alloy used for our nozzle was 16.2 watts per meter Kelvin. The temperature of the liquid nitrogen that would be flowing through the nozzle was negative 196 degrees Celsius, and then the ambient lunar atmospheric temperature that we used was negative 130 degrees Celsius. With these 3 parameters and the 3D model that we had generated, we were able to perform an ANTHA simulation of the flow through the nozzle to determine the temperature change as well as the temperature flux through the nozzle. Based off of the analysis, we found very minimal temperature changes, which means there would be a very negligible impact on the material's properties. This demonstrates the safety of the material that we chose and of our overall design. And for our model, we used the temperature of negative 100 degrees Celsius for the lunar atmosphere, but this can vary based on time of day and location. So we ran multiple simulations at a plethora of different temperatures, and all of them had very minimal differences between them. So all in all, we determined that the inherent thermal insulation of our design was enough to mitigate having to add additional insulation to the nozzle. And then one thing that we didn't analyze was the potential effects of the low temperature liquid nitrogen to the interior of the fuselage. However, the tanks, pipes, and valves that we chose were all designed specifically for the extreme conditions of the liquid nitrogen, so it would not be a concern. All in all, the lunar landing phase is crucial due to the rapid temperature changes and environmental changes that occur. Exposure to the lunar environment can cause temperature stresses on the spacecraft, and the very thin atmosphere on the moon can also create an increased vulnerability due to rapid temperature shifts. But all of these problems are accounted for with our design's inherent thermal insulation.
Hey everyone, I'm Trevor, and now that you've seen some on the structural analysis, we thought it'd be prudent to talk about the electrical and control aspects of our design. So electrically, we assumed that the biggest the biggest point that would take the most power would be the actuators attached to the nozzles. So conservatively, based on the statistics on the website of the AMS stepper motor, we found that at 6 watts per nozzle multiplied by 50 nozzles, that's about 300 watts used on descent and ascent from the lunar surface. What does this mean in the context of spacecraft power consumption? Well, according to a NASA document, well, we don't have the exact HLS specifications at this moment because it's still in development. So using NASA documentation on common satellites and spacecraft, we determined that the average spacecraft power consumption is between about 300 watts to 2.5 kilowatts. At this moment, with no additional power sources to our system, we believe that this falls into an acceptable range of power usage on ascent and descent from the lunar surface. And also, as you can see here, we have a basic electronic schematic connecting the gimbal / actuator and the nozzle valves to the onboard computer of the HLS. But what if we do need additional power? Well, our team took the liberty of estimating the power output that would be provided by the onboard solar panels of the HLS. Now, again, this is not public information, so we had to go off of speculation and what we know from modern technology. But what we did was, using renders, we calculated the area of the solar panels, and then we took the wattage and area of the ISS solar panels as an example. Combining these facts, we were able to calculate an estimated solar output of 27 kilowatts from the solar panels on the HLS. To be conservative, assuming half of it was in the shade, we provided a value of 13.5 kilowatts. Now, again, if we take into account what may be the power provided by the HLS satellites, you can see that we are well within the conservative estimate of how much power our motors will take on board of the HLS on ascent and descent. So at the moment, our team does not believe that this will be a large problem if implemented. Slide. And one last concept is we're going to touch on is a little bit of our control system. So the way the flow chart of our control pattern is that a lunar altimeter talks to the onboard computer. We want the nozzles to rotate on ascent and descent to mitigate potential plume created actually by the liquid nitrogen. So as it descends or ascends, the nozzles will slightly rotate. This computer will then talk to the nozzle actuator motors, which will then rotate, and the computers will then know that rotation. Compared to, say, multi-axial arms or anything of that nature, we don't believe that this control scheme would be all that complex. We have an input of the altitude relative to the lunar surface, and an output of the nozzle actuator angle. And so we believe that potentially a PID controller could be used for this system. We don't have exact control gains for you at this moment, but we can provide that in the final report. Thank you.
You guys clap for yourself.
We do repairs.
Great job.
Does anyone have our time?
You're like a minute or two over.
Okay.
Yeah.
Awesome.
Good job.
We were doing it right before this, and we cut some stuff out.
Our first one was 26 minutes, and our second one was like 31. So we were like, oh, we don't know. My sister was like really stressed because she doesn't want to ask us a question that will like be too hard for us. Her question was, how is the landing site selected? So I mean,
That's not our
what a timeline would be, and I said like that also that would depend on, we would need more information to determine implementation of our system.
You can stop sharing.
Oh.
We need to record everything.
Did you want to ask questions first? You want me to ask questions?
What are we talking?
Okay.
It's not sharing.
Just
Oh, you don't want to share.
Do you want to
Wait, do we want to share?
No.
Yeah,
Yeah,
Oh,
so
no,
they're picking
questions,
questions, right?
Yeah.
Oh,
yeah,
okay.
yeah.
I understand.
Yeah, I would rather, I'd like to see the slides while I'm talking about
Here,
that, so.
I got it.
I was just gonna.
Because you have to. Present it. You want to just do this or like the
Yeah, I thought we'd save
presentation?
this, we can.
No, just
scroll
do that.
through.
Okay,
You need to share screen. I don't see the sharing screen here.
Yeah, yeah.
Just share.
sorry, my bad.
There you
Could you go to the slide with those dolls and the outfits?
go.
I have no idea what I'm looking at. You didn't describe anything, what they were, what the difference is between the two. I just see one in light and one in dark clothes. What am I looking at?
Yeah, hi, sorry, so essentially the first doll is the team at Washington State University put dust on a fabric which simulates like spacesuits, and they put it in a vacuum chamber, and they treated it with a liquid nitrogen spray, and then they measured the amount of dust before and after the treatment, and they found a 98% reduction rate.
Sure, but which is which?
So yeah, the one on the left is,
You need to make sure that people like know this stuff.
Yeah.
I have no idea what I'm looking at.
okay, I'm sorry.
No, it's, no,
Yeah.
don't be sorry. I'm just saying.
Yeah, the one on the left is the one covered in dust, and then the material is black.
Okay,
So-
okay, gotcha.
Yeah.
Why exactly nitrogen as opposed to anything else?
Because of the study.
Because of the study.
Yeah,
We
exactly.
use that as the. It was basically like that. We were on the first week, we were just researching, and then one of the ideas was, well, this liquid nitrogen works at getting dust off of spacesuits. Could it work at also mitigating the dust while landing?
Okay. Oh crap, I just missed my meeting. Oh well, that's okay. Anyway, sorry. What's next? That just threw me off entirely. What exactly is your the rocket cycle you're using for your nozzles here? Like, are you using just like a pressurization? or-
Yeah, it's just a plenum connected to a nozzle, basically. There's no cycle or anything.
Don't you think you need pressurization in order to maintain the same amount of?
So for that, that's why we have the pressure. If you go to the fluid system, we have the building coil to keep the system, the pressure within the tank the same.
Oh, okay.
And, oh no, it's up.
missed the diagram.
It's this one right here.
It's the one all the way to
Yeah, and then so also we have the pressure reduction valve, which will actually reduce the pressure within the line to be less than the pressure in the tank. So we're not actually using all the pressure all the time.
Yeah.
We're reducing the pressure in the line so that we do, the pressure in the tank is still at a higher pressure than what's in the actual line.
Okay. And since you're working with cryogenics, a big problem with a lot of that kind of stuff is dealing with the fact that a lot of your gases will end up in being induced in some sort of phase change. Will that be able to mitigate this, or will you have to? You have to discharge.
So this specialized tank right here, this has two different outputs on it.
Mhm.
One of them is for liquid nitrogen, and one of them automatically turns it into gaseous nitrogen.
Mhm.
So it's stored as a liquid, but we take it out as a gas. It
And
does,
the tank also has a pressure relief valve.
yeah,
So that, just in case the nitrogen exceeds like the 100 kilopascals, then there is that pressure release valve which will.
Where will it be exhausted to?
There was a system that exhausted out into the atmosphere, but we didn't discuss that as much.
Okay.
So we were gonna look back at that.
Okay, that's also an important thing to consider.
Mhm.
I say there's a few other things on my mind. I'm still a little bit confused about your design. Like, what exactly is the base plate is connected to? Is the base plate the outside of the craft? Is that We what can go into the CAD. Yeah, just go to the CAD. I was a little bit confused on that. Yeah, so what you're seeing like on both images is the interior itself. Like the base plate is the outside of the stainless steel of the HLS. So it is, okay, so it is the outside. So when you're referring to some of the gimbals in the system, is there a gimbal feature here? or is that-
yeah, it's the motor right
That
there.
is the motor? Okay.
Yeah, it'll
That's-
rotate the entire thing outwards.
And that's the only gimbal involved? You don't
Yeah,
use any of
that's
that?
the only
So
gimbal
I
involved.
was like, why did you need a gimbal if you have all 50? But that makes more sense.
Yeah.
It's only one direction.
Yeah.
Because since the spaceship is mounted on the top of the spaceship super heavy, right?
Mhm.
We thought about just having the nozzles out, but then we were like, oh, we don't want it to go through the atmosphere, leaving Earth outside of the spacecraft. So we wanted to integrate it into into the spaceship, so it would be like flush along the side and would keep the aerodynamic and structural properties.
We also didn't know like how it would impact the implementations like on the rocket and stuff like that. So we wanted it to be seamless with like the design that we were given.
Gotcha. That makes sense. And what's the point of the square cross section
Where?
of the nozzle?
Oh, of the nozzle?
Mhm.
There is no point. It's just that was the way I found to get the greatest wake.
Greatest wake.
Like the greatest wake of the nozzle, like the most amount of spread,
Oh, I see.
like this. So that was the way that I was able to get the most amount of spread out.
Okay. I think there might be some issues with that, but I can't think of it on top of my head. So this is like the cross section of the long way.
Yeah, so it's like if you're looking at it from the top down,
Oh,
and there's the half.
gotcha.
Yeah.
Okay. And by spread, you mean just general, just.
Yeah, the wake.
Yeah.
So the wake, like you see all the way at the edge here.
Mhm.
This is what I would consider the edge of the wake,
Okay.
and the radial, not the radial direction, but the longwise direction.
Is that a boundary condition?
So at the end, like, this is actually cut off.
Yeah.
There's more that way, but that's when the wake stopped, and I didn't feel like it needed it. At the end of the boundary condition, it's basically like an outlet boundary condition, but
Okay.
it's to the.
So it's not a wall.
Yeah, it's not a wall. It's not a wall.
Here. Hmm. You don't need a phase change of the nitrogen? Is you just spraying it as a liquid?
Yeah, we're just no, we have it liquid stored, but it comes out of the tank as a gas.
The gas use.
Yeah.
One of the aspects of the tank is that it has a gas use valve, so it will
Yeah.
expel it as a gas.
Does that require any power for that?
No, it doesn't. It doesn't.
Okay. Could you scroll down a few more slides?
Yep.
There's something else. Let's go down a little more.
Should have page number.
Okay.
Page numbers are necessary.
That's a good
Okay.
Oh, right, force analysis.
Yeah.
So you've measured the force of the nozzle to be 190 newtons per nozzle, right?
Yes.
So do you, so you're having 50 nozzles, that's quite a few nozzles. Do you think that'd be appreciable and might actually cause issue in terms of landing sequences?
So we determined it's actually a good amount of force, but it's also technically in the direction of the force that the rocket plume is going.
Mhm.
And at the same time, we determined that there could be problems with stability, such as the nozzles were eccentric from each other. Well, we try to limit the amount of eccentricity as much as possible so that they would cancel each other out and the rocket would not spin. And at the same time, we also determined we believe that the stability already present in the rocket would be able to counteract the forces caused by the nozzle.
Okay. Yeah.
That's also a reason why we have all the valves, is so that if one of the nozzles fails and it doesn't create a force imbalance.
Yeah.
Okay. And
The
you have that
computer
as part
will-
of your control
Yeah.
system?
Yes. Yeah.
I didn't really see that in the presentation, but I see where you guys are coming from.
It's mostly in the fluid system, because we talked about
Oh, okay.
the pressure that each of them have a pressure gauge on the outside, so we can determine if the nozzles are working correctly, and if they not, that the quick release valves can be shut off.
Gotcha. Okay. Scroll down a little bit. No. A little bit more. Maybe not, maybe go back up. Oh, there's something else I was just thinking of. Oh, in terms of the cost, it would be really nice to have a breakdown of your cost analysis, because I only saw the one number, and that's not gonna be enough. You guys are gonna wanna have to like make sure you really lay out exactly where you're getting your numbers from.
Yeah, that
In
makes
terms
sense.
of, in terms of totals.
We just didn't do it. We just
Yeah, we just didn't want to put it all up in the
just got a
slide.
spreadsheet up there.
Yeah.
But at least have just a few data.
Okay.
Okay.
Because when you just have the one number, no one really knows exactly where you're putting all your money towards. And that's
Okay.
just a little confusing, so.
Yeah.
Okay.
But that's pretty much everything I have, that I can think of. so.
Those figures will definitely be detailed in the report.
Sure.
Yeah, there's just more so for aesthetics on the slide.
Okay.
Yeah, I want to say
Okay.
that the slides and everything, it's very comfortable to read because, there's some stuff that's like to be decided. And also, I'm glad that, I think I need to put comments in all the previous presentation that for the overview and for like each topic, make it very clear logic to narrate. And I think you guys did a great job. And another thing is that the presentation itself is really and for the details, I think can you go to the structure analysis?
Yep.
The maximum share model to web support, model to base support, why they're the same?
I'm sorry, can you say that again?
So, model to web support, is 0.526,
Yeah,
and model to base support is why, I'm.
So- yeah, so, we did the calculations for, there was we chose a point, at the back here, it's easier for me to point. So from where we had the force originating, we chose like the point of max interest to be like right back here. I did the calculation for the base support.
Yeah.
We chose it right back here.
Yeah.
And so the only real change from the two calculations is the distance from one to the other, and that distance wasn't too big, and so
There should be some difference.
Yeah. The difference is actually caused because the stress of the B one is multiplied by a factor because it's on a weld support.
that too, yeah.
That's what we did. So we multiplied this.
I think it's good to point out that B is a weld and C
Yeah.
is part of the plate under it.
Yeah.
So it's not
Yes.
welded.
Okay,
Yeah.
So they have different physical.
Yeah,
properties.
Right,
exactly.
but the calculated final result happen to be exactly the same. 5.265. Oh, 5.265.
No, yeah, they're
Yeah,
different.
they're just
Yeah,
slightly
they're-
different.
Yeah, they were slightly different. It's just that we're working with such small forces
Exactly.
that the real problem was in the significant digits and
Okay.
the insignificant digits.
And also checking the like maximum shear stress and also the level shear. Don't you guys feel like your structure is not optimized?
Oh yeah,
And so-
so yeah,
It's over.
yeah, it's over.
We did point that out when
We-
we were,
yeah.
because I was like, it could definitely be improved, but
The thing is that the metal that is there is not there for structural, really. It's more there to for at least for the nozzle is to hold the nozzle in place so that it doesn't move. It's not really
Well, I can make a thinner structure to.
yeah, but if
Yeah.
we got just kept going thinner and thinner, then it would be so thin that it would cost more to make based off of how thin it is, like the manufacturing. Like we could have made this super thin, and we could have because the factor of safety is insane. But it just the thinner and thinner we would make it, the more expensive it would be.
Not to mention, there's also like a lot of unforeseen variables when you're dealing with, like these missions where, it's on rocket, it's going up into space.
yeah, that's why factor.
But that's
safety.
Yeah,
Yeah.
that's factor of safety.
We could definitely make it smaller.
Because if you consider anything that like spacecraft design is about minimizing the weight.
Yeah.
And if I see something like 0.5 and the other way is like more than 100, there's something wrong here. Right?
Mhm.
And also for the thermodynamic calculation, PRLJ, are you calculating shear stress? Caused by torsion?
Yes, I do believe that is what I did.
Is that for A?
Hmm?
Is that for A point?
Yeah, yes. No. It's for the motor itself.
For motor itself?
Yeah.
So one thing is that, in solar links, we never use sigma for shear stress.
Okay.
Sigma is always normal stress.
Mm.
If shear stress, put it out there, otherwise it confuse everyone.
Yeah.
Okay.
My bad.
And I think it's the same thing here.
Yes.
I mean, you have 6 megapascal and then you have 500.
But I mean, like that's the motor, right? Like we could make our own motor for
Yeah.
sure.
Yeah, we just took, we found a motor that was adequate for the job, and then this ended up being, but the motor was still very adequate for the job, so we could probably optimize the motor, but we did take that into consideration.
Because the motor also had to be space approved, so we couldn't
Yeah.
just choose like any old motor.
Okay, next. think it's the. Power requirement,
Yep.
yeah, so, yeah. So you list, like information from somewhere, and then you have your own estimation. How did you
Yeah,
have your own estimation?
yeah, sorry. So I should have made that more clear on where I got my sources. So and this was, we determined this from the SpaceX renders, such as here. We literally, we know the dimensions generally of the HLS. So we use that to estimate the areas of the solar panels. So we created this one ourselves. This is a known factor from the ISS, should have made that more clear from NASA. And then these we calculated using these two pieces of information. So I could have clarified that these we calculated, and this is a known quantity.
That was in one of our PowerPoints,
Yeah,
actually, like.
yeah, actually, you're
report.
right. This was in one of the PowerPoints.
Yeah.
We took,
Lectures.
so the ISS, the ISS numbers, we pretty much knew. It was just a matter of estimating the square meterage of the solar panels on the HLS.
And
And
then we
then
just multiplied the two numbers.
Yeah, I should have made it more clear. I should have put a citation here on where we got that information. But
But
the rest of it, we calculated ourselves using the renders.
It's a very conservative
Yeah.
estimate because the solar panels that they're using for the HLS are supposedly much more advanced than the space station ones, so they would be generating even more power than we found.
Okay,
but bottom line, even with the conservative estimate, we're still well within
Our system
like
doesn't
the
take
range, yeah.
a lot of power.
okay. I think that's all, and also, it's like, you're done with this part and then it's end. I mean, you guys did a very good job, like overview and each topic and this this is slide for that. Why there's no conclusion at the end?
Oh.
Thank you for watching.
Thank you.
That's true.
Okay.
Okay, thank you.
Just all the questions, and I think you guys did a very great job.
Okay, thank you.
Thank you so much. We worked hard.
Yeah, and the presentation slides and everything and the work, the detailed work, everything is really great. Yeah.
Thank you.
Okay.
You like our report?
I love all of these videos. I like all of them.
Yeah, I didn't say you did it.
Everybody can watch it on the video.
Yeah, but we.
And there's 101.